Hello everyone. We want to introduce our work titled Mesh Mamba, a unified state space model for saliency prediction in non-textured and textured meshes. We come from Shanghai Jiao Tong University. In 3D visual perception, geometric structure and texture information are critical factors in determining how the human eyes capture and interpret object features. Together, geometry and texture create a comprehensive visual representation that shapes visual tension distribution and efficiency in object recognition. A deeper understanding of the interplay between these factors sheds light on understanding how the human eye processes complex 3D environments, offering insights that can guide model design to improve the overall visual experience. Therefore, we finished this work about mesh saliency. The mesh saliency dataset to systematically capture saliency differences across contrasting visual context. Specifically under textured and non-textured conditions, a mesh Mamba, a state space model for saliency prediction, in engineering to accommodate complex geometries and textural details, adaptable to the diverse visual stimuli and perceptual cues, and a novel subgraph embedding approach that mitigates topological disruption from spatial clustering, preserving enhanced positional relationship and geometric integrity. A bidirectional SSM for global context modeling that enables the comprehensive interaction across token sequences, bridging local geometry with texture channels. We first construct a peer saliency dataset of non-textured and textured meshes, collecting different saliency distribution of the same models under non-textured and textured conditions. In the eye tracking experiment, participants are randomly assigned to either the non-textured group or the textured group to view the experimental study. Based on the saliency prediction task under the two conditions, we propose a state space model for saliency prediction called Mesh Mamba. It mainly consists of a graph convolutional encoder, a subgraph embedding block, and a mesh block, and a Mamba block. The graph convolutional encoder processes the implicated texture features and the geometric features through graph convolution, enabling the preservation of topological structure of agency relationships. Subgraph embedding is designed to accommodate the difference in data formats handled by various Mamba family network. For example, Vision Mamba process 2D image by dividing them into patches based on pixel position, while Mamba 3D handles point cloud data by applying farthest point sampling, followed by the clustering to form coordinate-based groups. However, mesh data differs significantly from both formats. To address this, we adopt farthest point sampling to extract central points of local regions on the mesh surface. Then we apply a random walk sampling approach that iteratively traverses adjacent face, allowing us to preserve richer topological structure. The resulting subgraphs are then encoded with positional embeddings, enhancing the network's ability to capture global context and structure awareness. Following this, the Mamba block first applied the feature diffusion and aggregation operations to each node and its neighboring positions, effectively enhancing the receptive field of the local features. Then the bidirectional state space model block processes the contextual information of each element in the sequence from both directions, enabling a more comprehensive understanding of each token's position and its relationship within the global context. Finally, to adapt to the dense prediction nature of the Saliency task, a weighted feature propagation strategy is used to interpolate the central features of each subgraph block back to the entire mesh. This allows the network to compute the final saliency prediction value for each face on the surface. Then we conduct an experiment of saliency prediction for non-texture meshes. Then we give some qualitative results and visualization results. Then the experiment of saliency prediction for text meshes is also conducted. Then we give some performance evaluation on source 3D dataset, and we also present some models, our models flops analysis, and we also give some ablation study. Then we present this discussion on saliency-based simplification. Mesh saliency result with quadratic-based algorithm and saliency-based simplification. We show some visualization comparison of the original model with over 30K faces and its simplified version at 8K and 4K face mount.